Ever find yourself trying to do a million things on your computer at once, like streaming a movie, while also downloading a huge file, and maybe even trying to edit a photo?
It's a recipe for disaster, right?
Totally. But somehow, most of the time, our computers handle it.
It's incredible when you think about it. It's like they're juggling chainsaws of data and code.
And amazingly, most of the time, they don't crash and burn. So today, we're diving into the fascinating world of operating systems to uncover the magic trick, scheduling.
And what's really mind-blowing is that it's not just about deciding which task to do next. It's about managing a complex system where multiple processes are all vying for the same resources.
Right, like a digital free-for-all. So before we get into the nitty-gritty, let's define what we mean by a process, because that word gets thrown around a lot.
Absolutely. A process is essentially a program in action. So when you open your web browser or start typing a document, you're initiating a process. And each of these processes needs its turn to use the computer's brain power, the CPU, to actually get things done.
Okay, that makes sense. But with potentially tons of processes running at once, how does a computer figure out who gets to go first?
That's where scheduling comes in. And it's not just one thing, it's a two-tiered system. A bit like managing your to-do list, but on a much faster and more complex scale.
Two-tiered, so it's not just one big chaotic to-do list.
Not quite. Imagine this. You've got your long-term scheduling, which is like planning your month, right? Deciding which big projects or tasks you'll tackle. Then there's short-term scheduling, which is more like figuring out what you're going to work on right now, answering emails, finishing that presentation, maybe grabbing a coffee.
So long-term is the big picture, and short-term is the in-the-moment juggling act.
Exactly. And just like when you're juggling tasks, sometimes you have to reprioritize. And that's where the concepts of preemptive and non-preemptive scheduling come in. That's how the computer decides which process gets to go next.
It's that whole polite line versus a chaotic crowd thing, right?
Exactly. Imagine a line at a popular food truck. Now, non-preemptive scheduling is like letting everyone patiently wait their turn. Each person gets to order their food, finish up, and then the next person steps up.
Very civilized, very orderly. But computers aren't always so polite, are they?
True. That's where preemptive scheduling comes in. It's like if someone with a life-threatening allergy needs to cut the line to order, because even a moment's delay could be critical. In a computer, this happens when a high-priority process needs immediate attention.
Like when you hit the emergency brake on your self-driving car, right?
Exactly. So it's not just about being polite. It's about knowing when to interrupt.
Okay, so it's not just about being polite, it's about knowing when to interrupt. But how does the computer actually know which processes are like the emergency brake situation?
Good question. It all comes down to something called priority. Each process is assigned a priority level.
Kind of like a triage system.
Yes, exactly. And this is based on several factors. How urgently it needs that CPU time, what its deadline is, even how long it's been waiting patiently.
So if I have a deadline looming and I haven't saved my work, the save process is going to get bumped up the priority list.
Precisely.
It's like my computer knows I'm about to have a meltdown.
Exactly. Now imagine two processes with equally urgent deadlines.
Yeah.
How do you decide who goes first?
Ooh, that is a tough one. It's like those moments when you have a million things to do and they all feel equally important.
This is where what's called the arbitration rule comes into play. One common method is round robin.
Round robin. What's that?
So the computer gives each process a small slice of time to use the CPU and then moves on to the next one, making sure no one process hogs all the resources. It's like spinning plates.
A little attention to each one in turn to keep them all going.
Exactly.
That makes a lot more sense. So we've covered how the short-term, in-the-moment scheduling works. What about that long-term, big-picture planning?
Yes. Long-term scheduling is less about that immediate action and more about resource allocation over a longer period.
So if I'm understanding this right, it's like deciding which apps get to be open and running in the background, even when I'm not actively using them.
Exactly. It's about ensuring the system as a whole runs smoothly. Imagine you're launching a resource-intensive program, like, let's say, some heavy-duty video editing software. That needs a lot of memory, a lot of processing power.
Right.
Long-term scheduling helps determine if the system actually has enough resources available, or if it needs to free some up. And that's often why you might see your computer slow down a bit when you have a lot of programs running simultaneously.
So it's making those tough decisions about who gets what to keep everything from grinding to a halt.
Precisely. And this constant juggling act, these millions of decisions happening every second, they impact everything, from how fast your computer feels to how smoothly your favorite apps run.
It's kind of mind-blowing when you think about it. This whole hidden world inside our devices that most of us never even consider.
It really is.
Yeah.
So next time you open a new app or stream a video, just take a moment to appreciate that intricate dance of scheduling happening behind the scenes.
A dance that's keeping our digital lives moving to the rhythm of ones and zeros. Okay, so you're ready to dive deep into batch processing scheduling algorithms. Want the inside scoop without drowning in technical jargon? Well, you've come to the right place. We're breaking down everything you need to know about how these algorithms work, why some are built for speed, while others prioritize fairness, and a few try to find the perfect balance.
It's a lot like finding the perfect traffic system. You want efficiency, of course,
Yeah.
but you also need to make sure that everyone gets where they're going, without getting stuck in a digital traffic jam.
I like that analogy. But before we hit the road, let's make sure we're all on the same page. We're talking about batch processes, like those tasks your computer's handling in the background without you even lifting a finger. Things like payroll processing, weather predictions, all that good stuff.
Exactly. And the beauty of these processes is that once they're initiated, they just run their course, no babysitting required.
Which is great, because who has time for that? But, and this is where things get really interesting, hey, there's not just one way to schedule these processes. It's like having a toolbox full of different scheduling algorithms, each with its own, shall we say, quirks, advantages.
Yeah, and choosing the right tool for the job. It can make a world of difference in how smoothly your system runs. And today, we'll be looking at 3 of these tools: FIFO, SJF, and SRT.
Yeah, our sources focus on these 3. They sound a bit like a robot boy band, don't they? But don't let those names fool you. There's some serious computer science happening under the hood. So, hit us with your best shot. What's the deal with FIFO?
FIFO, or first in, first out, is, I guess you'd say it's the reliable one of the group.
Yeah.
Think of that friend, the one, who always insists on doing things in the exact order they were planned. Even if there's like a faster, more efficient way to do it, well, that's FIFO. The first process in line is the first one to get processed.
Simple, straightforward, no cutting in line allowed. But what about those times when we need a bit more pep in our step? Is that where SJF comes in?
Exactly. Shortest job first is all about speed. If you could pick the shortest line at the grocery store, wouldn't you? Well, that's SJF. It's always prioritizing the quickest tasks just to keep things moving.
Sounds pretty efficient. So why wouldn't we want to use this all the time? What's the catch?
Well, imagine you're that person at the deli counter, the one who ordered the really complicated sandwich, while everyone else is just grabbing a drink. With SJF, you might end up waiting, well, forever, because it's so laser-focused on speed that those longer processes, they can end up getting pushed aside.
So it's like a fast-moving express lane
Yeah.
that can actually leave some folks stranded. Okay, that makes sense. So we've got our simple and straightforward FIFO, our speedy SJF. Where does SRT fit into all of this?
Well, think of SRT, shortest remaining time, as the more adaptable, dare I say, clever cousin of SJF. Still interested in speed, but it takes a more dynamic approach. SRT is constantly reassessing which process has the least amount of time remaining and prioritizes that one.
So instead of just looking at the initial size of the task, it's constantly reevaluating and adjusting on the fly.
Precisely. SRT allows a process to be interrupted, put on hold, and then resumed a little bit later.
Yeah.
Which is incredibly useful for making the entire system more responsive.
That's incredible. I never realized how much thought goes into something as seemingly simple as scheduling tasks. But I have to ask, how does SRT predict how much time is actually left for each task? It's like having a crystal ball for your computer.
Yeah, it's not magic, but it is pretty clever. SRT uses, some math. It looks at past performance to make an educated guess, really, about how much time a task is left.
So it learns from experience, like, okay, this type of task usually takes about this long.
You got it. It's always analyzing, constantly adjusting its predictions.
Yeah.
Based on what it's learned.
That's amazing. Okay, so we've got FIFO, our stickler for order, SJF, our speed demon, and SRT, the adaptable one. But this is all well and good, from a technical standpoint. How does it actually play out in the real world? Where will we see these algorithms in action?
Well, FIFO, with that straightforward approach, it's often used in systems where order is, paramount. Think print queues, for example. You really don't want to mess up the sequence of jobs there. Or even simple to-do lists, where you're just checking things off one by one.
Makes sense. First in, first out, no favoritism. What about an SJF?
But SJF, with its need for speed, You'll often find it in situations where minimizing the overall processing time, it's critical, like a web server,
Yeah.
handling tons of small requests from users.
Yeah.
By prioritizing those quick tasks,
Yeah.
it keeps everything feeling snappy and responsive.
So that's why websites load quickly. Okay, that makes sense. And SRT.
SRT, with all its adaptability, it really shines in those situations where responsiveness and user experience are key. Imagine an air traffic control system, constantly needing to adjust to changing conditions and prioritize those time-sensitive tasks. That's where SRT really comes into its own.
Wow. So these algorithms are working behind the scenes in some pretty important places. You're making me look at my computer in a whole new light. But let's talk about downsides for a sec. We touched on how SJF can lead to longer processes getting stuck. Is that what starvation is all about?
Exactly. Starvation happens when a process keeps getting pushed aside, you see, because those other shorter processes just keep jumping ahead of it. It's like being stuck in a never-ending line because someone keeps cutting in front of you. Ouch. That doesn't sound fun at all. So how do we avoid this digital Hunger Games scenario? Is it all about just finding that perfect algorithm, or is there more to it?
It's a bit of both, actually. While choosing the right algorithm is important, for sure, it's also about really understanding the trade-offs involved. And sometimes you even have to tweak the algorithms themselves. We need to remember, efficiency, it's not just about speed, right? It's about finding a balance between speed, fairness, and in some cases, even predictability.
There's that P word again. You're really piquing my curiosity now. What's so important about predictability when it comes to these processes running in the background?
Yeah.
Predictability, it's like, knowing when that launching machine is finally going to be free. And we're talking about these background processes on my computer. It's a great analogy because sometimes, just like in life, in computing, a consistent rhythm, it's actually preferable to just raw speed. Think about those times when you're juggling a million tasks and then bam, some random interruption throws everything off. Predictability, it helps us avoid those digital hiccups.
Okay, so it's about maintaining this smooth, this consistent flow, even if it means like sacrificing a little bit of speed. Are there specific scheduling methods that are designed to do that, ones that put predictability front and center?
Absolutely. And this is where things get even more interesting. We can introduce things like priority queues. So certain processes, they're given like a higher ranking based on their importance or how sensitive they are to delays.
So it's like having a VIP line for those time-sensitive tasks.
Yeah.
Making sure they don't get stuck waiting.
Yeah. Exactly. And then there's, real-time scheduling. Now that's a whole other level of complexity. Imagine a self-driving car. Those split-second decisions, they're absolutely critical, right? Real-time scheduling, it's designed to guarantee that those critical tasks, they're handled within a very specific time frame no matter what.
Wow, that's next level stuff. So we've gone from simple lines at the grocery store to self-driving cars. I knew there was a reason. I love this show.
Yeah.
But seriously, this has been eye-opening. It's amazing to think about all these different approaches to scheduling, and each one has its own strengths and weaknesses.
And that's really the key takeaway here, isn't it? There's no one-size-fits-all solution. Choosing the right scheduling algorithm, it all comes down to really understanding the specific needs of your system and prioritizing what matters most. Do you need raw speed, fairness for all those processes, or maybe that steady, that predictable rhythm?
It's like having a whole toolbox of scheduling strategies at your disposal.
Yeah.
You've equipped us to make informed decisions about how we want our digital worlds to run.
Precisely. And the more you understand about these algorithms, the better equipped you are really to optimize your systems and get the most out of your technology.
So there you have it. No magic bullet. Yeah. But a whole lot of food for thought. Next time you're waiting for your computer to catch up, you'll have a newfound appreciation for that intricate dance of scheduling algorithms happening behind the scenes. Until next time on The Deep Dive. All right, everyone, buckle up, because today we're diving headfirst into the world of operating systems.
That's right. And specifically, something that affects us all every single time we use our devices.
We're talking interactive process scheduling, folks. Get ready to find out what makes your app snappy or not so much.
Yeah, this is all about that behind-the-scenes magic that dictates how your computer juggles everything you throw at it.
We've got excerpts from this operating systems text, and let me tell you, it's fascinating stuff.
Oh, absolutely. It's like peeking behind the curtain and seeing how the whole system manages to give us this illusion of multitasking.
Right. Because let's be honest, our computers aren't actually doing a million things at once, are they?
Nope, not really. It's more like a really, really fast-paced juggling act.
So it's all about switching between tasks so quickly that we don't even notice.
Exactly. And that's where interactive process scheduling comes in. It's the system that decides which task gets a turn on the CPU and for how long.
Okay, so it's like a very bossy traffic cop, directing all the different programs and processes vying for attention.
That's the great analogy. And just like a traffic cop, the goal is to keep everything running smoothly and prevent any one program from hogging the road.
And the smoother the traffic flow, the faster our devices feel. But how does it actually, how does it work?
Well, the source talks about something called preemptive scheduling, which might sound a bit intimidating.
Yeah, preemptive does sound a bit forceful.
Right. It essentially means that the operating system has the power to interrupt the running process, even if it hasn't finished.
Wait, really? It can just, cut a process off mid-task? Seems kind of rude.
Well, it's for the greater good, trust me. Imagine a program just decides to go rogue and hog all the CPU time.
Oh, okay. I can see how that would be bad. Everything else would grind to a halt.
Exactly. That's where preemptive scheduling swoops in. It divides processing time into these little slices and gives each process a turn.
So it's like each process gets its own little time slot, and then it's someone else's turn.
You got it. And this ensures that even if one process is being a bit of a resource hog, others still get their fair share.
Okay, that makes sense. So we've got this system for dividing up CPU time, but how does the operating system actually decide which process goes next?
Well, that's where it gets really interesting. The source talks about all these different scheduling algorithms, each with its own strengths and weaknesses.
Algorithms? Sounds like we're getting into the nitty-gritty now.
We are. It's like different strategies for managing all those time slots we talked about. Let's start with the simplest one, round robin. Imagine a line at a bakery. Everyone gets their turn, one after another.
So each process gets an equal slice of CPU time, regardless of what it's doing.
Precisely. It's fair, straightforward, but sometimes fairness isn't always the most efficient approach.
Right, because some tasks are probably more urgent than others. Like, if I'm typing a message, I want that to feel instant.
Absolutely. And that's where something like multi-level scheduling, or ML, comes in. It introduces priority levels.
So, high priority processes get to jump the queue.
Exactly. Think of it like express lanes on a highway. Crucial system processes or tasks that directly impact user experience get to zoom through.
Okay, that makes sense. So if I'm editing a video, for example, that might get lower priority than something like responding to a keystroke.
Exactly. The goal is to make the system feel as responsive as possible, even if it means some background processes take a bit longer.
This is so cool. It's like our devices are constantly making these behind-the-scenes decisions to optimize our experience.
They are. And it gets even more sophisticated with multi-level feedback, or MLF. This algorithm can actually learn from how processes behave and adjust their priority accordingly.
Wait, hold on. It can learn. It gets smarter over time.
In a way, yes. For instance, if it sees that a task consistently uses up all its allocated time slice, it might lower its priority a bit to prevent it from hogging resources.
That's incredible. It's like having a tiny, super efficient project manager living inside our computers.
I like that. And all of these complex algorithms and scheduling strategies ultimately boil down to one crucial factor: response time.
Right. Because no matter how fancy the technology, if it doesn't feel snappy and responsive, it's going to drive us crazy.
Absolutely. And that's the constant balancing act that operating system designers face: how to make everything fast and efficient while still ensuring fairness for all those processes vying for attention.
It's a tough job. But on that note, we've reached the end of our deep dive for today. But before we go, one final thought to ponder.
Oh, yes. I love a good thought-provoking question.
The source mentions something called context switching, which is basically the process of the CPU switching between different tasks.
Right. Every time it switches, there's a bit of overhead involved.
Yeah, exactly. So here's something to think about. How might frequent context switching actually impact the overall performance and responsiveness of your device?
That's a great question. And one that I bet we've all experienced at some point, even if we didn't realize it.
Until next time, deep divers. Keep exploring, keep asking questions, and we'll see you in our next deep dive. All right, so we've all been there, right? Staring down the barrel of a deadline, that bill that's due, that project at work. Heck, even just remembering to text someone back.
Yeah, deadlines are everywhere.
They are. But imagine those deadlines were measured in, microseconds. That's what we're dealing with in the world of real-time computing, where any delay, no matter how small, can be a huge problem.
Absolutely. We're talking about systems that need to react instantly.
Exactly. And that's what we're diving into today. how computers manage to juggle all these tasks when even the tiniest slip-up just won't fly. And we've got some cool stuff to unpack, research papers, the whole bit.
Yeah, looking forward to it.
So let's get specific. We're talking real-time processes, but what does that actually look like? Think about something like a live concert being streamed online. You've got tons of data, video, audio, and it all has to be processed and sent out to everyone watching in, well, real time.
Right, any lag there and it just ruins the experience.
For sure. And that's where these things called scheduling algorithms step in. They're like the conductors of an orchestra, making sure everything happens right on the beat.
I like that analogy.
Right. So the research we're looking at dives into two main players in this world: rate monotonic, which is often shortened to RM, and earliest deadline first, or EDF for short. And forgive me if I get some of the details wrong here. I'm still wrapping my head around all this.
No worries. Happy to clarify anything.
Okay, cool. So from what I understand, RM is like that super organized friend we all have, the one who schedules everything based on how often it needs to happen.
Makes sense. The more frequent a task, the higher the priority.
Exactly. But then you've got EDF, which is all about deadlines. Whatever's due soonest gets bumped to the front of the line, kind of like how we cram to finish a project the night before it's due.
Huh. Yeah, that's a good way to put it. Though hopefully these systems are a bit more reliable than our late-night cramming sessions.
Hopefully. One thing that's really interesting about both of these algorithms is that they're preemptive.
Right, which means they can interrupt a task if something more urgent comes up. Responsiveness is key in real-time systems.
So, like, if you're cooking dinner and the smoke alarm goes off, you stop what you're doing and deal with the alarm first. You don't wait for the food to finish cooking.
Exactly. Or think about controlling a robot arm in a factory setting. If something unexpected happens, the system needs to react immediately, even if it means interrupting an ongoing task.
Gotcha. So it's all about making sure the most critical task gets the attention it needs precisely when it needs it.
You got it.
And speaking of timing, you mentioned earlier that these processes often have to work within incredibly short periods. Like, what are we talking about here?
We're talking milliseconds, even microseconds sometimes.
Wow, that's incredibly fast.
Yeah, it has to be. Think of it like a heartbeat. It has to happen within a very specific time frame to keep things running smoothly. And in these real-time systems, those time frames are incredibly small.
That's wild. So we've got these algorithms, RM keeping things organized by frequency, and EDF prioritizing those tight deadlines. But can they always, and I mean always, guarantee that every single thing will happen on time? The research I was looking at mentioned something called CPU utilization. What's that all about?
Good point. CPU utilization, or U, basically tells us how much of the computer's processing power is being used at any given time. Think of it like your own energy levels. If you try to do a million things at once, you're going to use up a lot of energy. Push yourself too hard, and well, you might not get everything done. You might even crash.
So if the CPU is maxed out, things might start to slip through the cracks.
Exactly. And this is where it gets fascinating with these algorithms. What's super cool about EDF is that as long as the CPU utilization is within a certain limit, it guarantees every single deadline will be met. It's like a perfectly taxed schedule where everything fits in just right.
So EDF really is the deadline master. So if it's so good at meeting deadlines, why would anyone ever choose to use RM?
That's a great question. EDF is fantastic at optimization, but it's not always the best choice in every situation. Remember how RM is all about the frequency of tasks. That actually makes it a lot more predictable in the long run. And there are some systems, like those that control things like power grids or medical equipment, predictability can be even more important than raw efficiency.
Ah, okay. So it's kind of a trade-off then. It's like EDF is the super efficient friend who always gets everything done last minute, but RM is the one you can set your watch by.
Exactly. And that's what makes this whole area of real-time systems so interesting. It's not just about finding the most optimal solution on paper. It's about understanding the specific needs of a system and deciding what's most important in that context. Sometimes a less optimal choice might actually lead to a more reliable and robust system overall.
Wow, that is a lot to consider. It's like choosing between a heart surgeon who's always on time but maybe a little less experienced, and one who's brilliant but, well, you might be kept waiting a bit longer. It makes you really appreciate the complexity of these systems.
It does, and that's what makes it so fascinating to study. It's a constant balancing act between efficiency, predictability, and the real-world constraints we have to work within.
Absolutely. Well, this has been a fascinating deep dive. Thanks so much for breaking down all these complex ideas.
My pleasure. Always happy to talk about real-time systems.
I bet. And for our listeners, I hope this is giving you a little glimpse into the incredible world of real-time computing. It's amazing to think that all this is happening behind the scenes, ensuring that everything from your live streams to your car's brakes is working exactly as it should. And hey, maybe next time you're staring at a deadline, you'll have a newfound appreciation for the algorithms working tirelessly to keep our digital world running on time. Until next time. All right, everyone, get ready, because today we're taking a deep dive into something most of us take completely for granted.
That's right. We're talking about something that's always humming away behind the scenes, making sure your digital life actually, works.
Exactly, we're diving headfirst into the fascinating world of operating systems, or as the cool kids call it, OSs.
Me, or more specifically.
More specifically, how they juggle everything we throw at them. Seriously, think about it for a second.
Yeah.
You've got browsers with like a million tabs open, music streaming, maybe even a game running in the background.
And somehow your computer manages to keep up with it all, usually without bursting into flames.
Usually. I kid, but seriously, how does it actually work? What kind of wizardry is going on under the hood to prevent total digital chaos?
Well, let me tell you, it's not magic, although it can feel like it. It all comes down to some seriously clever programming, specifically something called operating system scheduling. And that's what we'll be unpacking today, using some recent research on scheduling algorithms.
So, from what I understand, these algorithms are kind of like the conductors of an orchestra.
Love that analogy. That's a great way to put it, yeah.
Each instrument, or in this case, each program or process, needs its moment to shine without drowning out the others.
Precisely. And just like a conductor balances the flutes and the drums and the violins, the OS has to figure out which processes get to use the computer's resources and when.
And those resources, we're talking processing power, memory, stuff like that.
You got it. Those are the big ones. And if the OS isn't careful about how it doles them out, things can get very, very slow.
Or worse, the dreaded blue screen. So how does it actually decide who gets priority? Our research paper throws around some serious jargon, stuff like multi-level queues and priority aging.
Oh yeah, they love their technical terms, don't they? Don't worry, we'll decode all that. The key thing to remember is that not all processes are created equal, right?
Right, like editing a video is going to be way more demanding than just opening a text file.
100%. So one of the simplest approaches, which by the way isn't used much anymore, is this idea of a two-tier system. Imagine two lines, one for the really important stuff and one for everything else.
Two-tier, got it, like a VIP line at a club or something.
Exactly. Think of things like real-time applications, video calls, gaming, anything where a tiny delay could completely ruin the experience.
Yeah. Those go straight to the front, no waiting around. And then the general admission line, that's for your everyday tasks, like checking emails, browsing the web, that sort of thing.
You're getting it. The VIP processes get first dibs on the computer's resources, and then whatever's left over is distributed among everyone else.
Seems simple enough. So if it's so simple, why doesn't everyone still use this two-tier approach? What's the catch?
Well, as with most things in life, it's not quite that straightforward. Modern operating systems are dealing with way more complexity than they did back in the day. Imagine trying to direct rush hour traffic with just 2 lanes.
Yeah, good luck with that. You're going to need a much more sophisticated system.
Exactly. That's where things get really interesting. Instead of this rigid two-tier system, modern operating systems use something called floating priorities.
Floating priorities, that sounds way more complex.
It is, but in a good way. It's all about being adaptable, responsive to what the user is actually doing at any given moment.
Okay, give me an example. How do these floating priorities actually work in practice?
Sure. Imagine this. You're typing away on an important email, super focused.
Then there, the dreaded blinking cursor.
Exactly. Now, in that moment, the OS is going to prioritize anything related to your keyboard input. It wants to make sure that every keystroke registers instantly, without any lag.
Because nothing's more frustrating than that.
You got it.
Yeah.
But now, let's say you finish your email, and you want to download a huge file. You click the download button, and suddenly
the OS shifts gears completely.
Exactly. It recognizes that this new task, the download, is now the priority. So it starts allocating more resources to the download, maybe even slowing down some background processes to make sure things run smoothly.
So it's constantly analyzing, reprioritizing, making sure everything gets the resources it needs without bringing the whole system to a grinding halt.
That's it. It's all about being dynamic, adaptable, and constantly optimizing performance based on the user's needs, even if those needs change from one second to the next.
Which, let's be honest, they do. We are notoriously fickle creatures when it comes to our digital demands. So next time I see that little spinning wheel of doom,
You'll know that it's not necessarily a bad thing. It just means your OS is working overtime to juggle your requests. And hopefully, thanks to all those clever algorithms, it won't be spinning for long.
that's the dream, right? Seamless, invisible efficiency, all thanks to the magic, or should I say, the engineering brilliance of operating system scheduling.
I think engineering brilliance is a bit more accurate, even if it's not as catchy. But you know what I find really fascinating?
What's that?
This is just scratching the surface. As our devices become even more powerful, and as we demand more from them, who knows what the future holds for operating systems and how they'll keep everything running smoothly? That's something to ponder.
It really is. It makes you appreciate the incredible complexity hidden beneath the surface of our everyday tech, doesn't it? All right, everyone, ready to dive in. CPU scheduling, it's one of those things, you've got stacks of notes, tons of concepts swirling around.
Easy to get lost.
Exactly. So today, we're cutting through the noise. What really matters when you want your computer to run like a dream? What are the key things to focus on? That's our deep dive today.
And let me tell you, there's a lot more to it than just raw speed.
Yeah.
We're going to uncover some really interesting trade-offs, things you might not expect.
Right. Like I was looking at my notes earlier when we've got our big players. CPU utilization, throughput, turnaround time, waiting time, response time.
Usual suspects.
Yeah, but then there's response time variance, and that one always trips me up a bit.
Yeah, it's a bit of a mouthful, isn't it?
It is. But it's important. And something I noticed, just thinking back to my notes, there's this idea that just maxing out CPU utilization, like making it work constantly, isn't always the best thing, right?
Right, and you even highlighted something interesting in your notes. It actually said that sometimes pushing for the maximum throughput can have a negative impact on that response time variance we were talking about.
Yeah, and I was wondering about that because, my gut feeling is if things are getting done quickly, shouldn't the variance be low?
It seems intuitive, right?
Okay.
But think about it like a freeway. Okay, if you just cram as many cars onto that freeway as possible, yeah, it might seem like you're increasing the throughput, more cars are moving.
Right.
But the whole system gets way more fragile. One little fender bender, someone slams on their brakes, suddenly you've got a traffic jam going all the way back.
Oh, I see.
That's your variance going through the roof.
Okay, so it's not just about raw speed then. It's finding that balance between getting things done, yeah, but also keeping everything flowing smoothly.
Exactly. And that's where those other factors come into play. Your waiting times, your response times. I mean, we all love a fast computer, obviously.
Of course, who doesn't?
But honestly, having a consistently responsive system, wouldn't you say that's even more important than just blazing speed in short bursts?
100%. I'll take a computer that responds consistently over something that's super fast sometimes and then lags horribly other times.
Absolutely, and that's why you highlighted that bit about response time variance, right?
Mhm.
Especially for anything interactive. Think about that choppy video call example.
Ugh, the worst. Makes you want to throw your computer out the window.
The worst.
Speaking of things that make you want to chuck your computer out the window, my notes also mentioned how keeping the CPU busy doesn't always equal better performance. I found that interesting, especially the bit about context switching.
Yeah, context switching. It's like every time the CPU has to switch between different tasks, imagine it having to change hats.
Okay, yeah.
Just to put down what it's doing, find the new hat, get situated. That takes time.
Oh yeah, it does.
So even if the CPU is technically busy,
Yeah.
constantly switching can really slow things down overall.
That makes a lot of sense. It's like when I try to multitask too many things at once, I get way less done overall.
Exactly, you got it. And then, on top of that, you've got this whole other concept, process priority.
Yeah.
Which adds another layer of complexity.
Right?
It's not just about getting work done, it's about getting the right work done first.
So it's about prioritizing.
Exactly.
So I guess the main takeaway, if we're thinking about applying all this, is that there's not a one-solution-fits-all situations, right?
Nope, not at all.
The best scheduling algorithm really depends on what you're trying to achieve and the limits of the system.
100%.
It's all about context.
And that brings us to my final thought-provoking question. Your notes focus on average waiting time.
Right, as like a key measurement.
But what about situations where you need a guaranteed maximum wait time? Like imagine a system controlling something critical, maybe a heart pacemaker.
Oh, wow.
Averages don't matter so much then. It's the absolute worst case scenario you have to worry about.
That's true. That completely changes how you'd approach the problem. Wow. That's a really interesting thing to think about.
It is. It really emphasizes that context is king.
Couldn't agree more. And on that note, we're going to wrap up this deep dive. Hopefully, everyone listening is feeling a bit more confident, not just understanding the definitions, but really thinking about how this stuff plays out in the real world.
Absolutely. It's about understanding the nuances.
Thanks for joining us.
Thanks, everyone.
Ever find yourself staring at your computer screen? Like, how on earth is it doing all this at once?
Yeah.
It's mind-boggling. Well, get this. Today's deep dive is for you. We're tackling multiprocessor scheduling.
Ooh, juicy.
And trust me, we're going deep, diving into this intense operating systems textbook excerpt you sent us.
Yeah, it's a bit of a head-scratcher.
But don't worry, we'll break it down into plain English. No jargon overload, I promise. So, ready to unravel the mystery of how our devices juggle a zillion things at once.
Absolutely. What's especially fascinating is how the very definition of a multiprocessor has evolved, you know?
Oh, tell me more.
It used to be all about having multiple, physical processors, but now it's more about cramming insane processing power onto a single chip.
Right. It's like we've gone from a whole team of chefs to one, super-powered culinary robot.
Precisely. The excerpt talks about multi-core CPUs and multi-threaded cores. These terms point to a wild reality. A single chip can now have multiple cores, each managing tons of threads.
Okay, so my laptop that brags about its quad-core processor,
Yeah.
it's basically a mini supercomputer in disguise. That's wild. But how does it actually work?
Well, that's where multiprocessor scheduling comes in.
The maestro of the processor world, making sure everything's in sync.
Exactly. Without a conductor, even the most talented musicians would just be noise, right? This scheduler makes sure all those processors play together smoothly and efficiently. Decides which processor gets what task, and when that's what determines how fast or slow your computer feels.
So it's not just about dividing the work, it's about doing it strategically, making sure no single processor is overwhelmed. Kind of like, I don't know, air traffic control for your computer.
Perfect analogy. The excerpt dives into two main approaches to this, asymmetric and symmetric multiprocessing.
Okay, let's break those down. Asymmetric versus symmetric, what's the difference?
Well, asymmetric is like having one head chef who delegates to a team of cooks.
Got it.
It's simpler, but if the head chef gets swamped, everything slows down.
Makes sense. So what's the alternative?
Symmetric multiprocessing, or SMP, is like each chef managing their own station. Every processor can handle tasks on its own, way more efficient, much higher performance overall.
So instead of one stressed out chef, you have a team of pros, each owning their part of the process. I bet that's way more efficient, especially as tasks get more intense.
You're getting it. But SMP does bring its own challenges, mostly in how we organize and distribute those tasks, the threads, among all those independent processors.
Right, because we can't just throw tasks at them randomly and hope for the best.
Exactly. Within SMP, there are two main ways to manage the queue of threads: a common ready queue or private queues. Think of it like a common queue is like a single line at a crazy busy restaurant.
Oh, I know that feeling. Everyone's vying for attention.
Right. Now, private queues are like dedicated lines for each chef, way more streamlined.
So each processor gets its own line of tasks, no more bottlenecks, no more waiting around.
Exactly. Private queues are the MVPs, more speed, more efficiency. They're the go-to for most modern systems. But it's not just about speed. Private queues also play into this cool concept called processor affinity, which boosts efficiency even more.
Okay, processor affinity. Now that sounds intriguing. Do processors have feelings now?
Kind of. Imagine you're a chef, right? All your tools, all your ingredients, always in the same spot. Makes you work way faster, right?
Oh, 100%. Muscle memory, everything's within reach. So a processor develops an affinity for certain tasks because the necessary data is already stored nearby.
Bingo. It's called a warm cache. Less time fetching data from memory, more time actually getting things done.
Clever. But hold on, what about making sure all the processors are actually being used?
Excellent point. That's called load balancing. Making sure no processor is chilling while others are slammed. And it's a constant balancing act.
Because if one processor is drowning in work while the others are taking a coffee break, what's the point of having a multi-processor system in the first place, right?
Precisely. Load balancing keeps everything humming along smoothly, no processor left behind.
So it's like having, a kitchen manager who's constantly keeping an eye on things, making sure no one's overwhelmed.
Exactly. And just like different kitchens have different styles, there are different ways to do load balancing.
Which brings us to those push and pull migrations we've heard whispers about. I imagine it's like, are chefs handing off dishes, or are they asking for help when they're drowning?
Love the analogy. Push migration is proactively moving tasks from a busy processor to a less busy one, while pull migration is more like a processor waving its hand saying, "Help me."
This is amazing. So we've got multi-core CPUs, SMP, queues, affinity, load balancing, all this complexity happening just so I can open a web browser.
It's mind-blowing. And we're just getting started. Remember those multi-threaded cores we talked about?
Oh, right, like finding a secret room within a secret room, even more processing power hidden within each core. But before we dive into that rabbit hole. All right, so before the break, we were talking about those multi-core CPUs, like, whoa, layers upon layers of processing power. And you hinted at even more power hiding within each core. It's like those Russian nesting dolls, right? You think you've reached the smallest one, and bam, there's another one inside.
Exactly. And that's where multi-threading comes in.
Yeah.
Think of it this way, it's like squeezing even more juice out of each core, especially when you consider those pesky memory stalls.
Ugh, those annoying delays when your computer's like, hold on, gotta grab some data, and you're just sitting there tapping your fingers.
Precisely. Now, picture a juggler keeping multiple objects in the air at once. That's essentially what multi-threading does within a core. While one thread is stalled, waiting for data, the core can instantly switch to another thread that's ready to roll, so the core itself isn't just sitting there twiddling its thumbs.
So it's like having a single worker who can seamlessly switch between tasks. No time wasted, maximum efficiency.
Exactly. And that's where you get terms like hyper-threading. You've probably seen that one thrown around in processor spec.
Oh, absolutely. My laptop loves to brag about its extra logical cores, thanks to hyper-threading. So these logical cores are like virtual workers created through multi-threading.
You got it. It's like magic. A single physical core can act like multiple logical cores. Some processors can have dozens of these logical CPUs, even with just a handful of physical cores.
Okay, my brain's trying to keep up, but I have a feeling it's not as easy as just having a ton of threads, right? There must be some method to the madness.
You're right. It's not just about quantity. It's about strategy. The excerpt mentions coarse-grained and fine-grained multi-threading. Basically, how often the core switches between threads.
So, like, coarse-grained is switching tasks every hour, and fine-grained is switching every few minutes.
That's a great way to think about it. Coarse-grained happens less often, usually triggered by events like, you guessed it, memory stalls. Fine-grained switching happens much more frequently, even at the end of every instruction cycle.
I'm sensing some trade-offs here, like one's easier but maybe not as efficient.
Exactly. Coarse-grained is simpler to implement, but it might not be as responsive. Imagine having to wait a whole hour to switch between emails, right? Fine-grained is more complex, but it can squeeze out more performance, no wasted time.
Wow, even at this microscopic level, it's all about finding that sweet spot between complexity and efficiency, like a perfectly synchronized dance.
And speaking of a delicate dance, remember our chat about processor affinity? How important it is for a processor to have quick access to its data.
Right, the warm cache, having the data nearby, ready to go.
Well, this is where things get even wilder with UMA non-uniform memory access.
Okay, INME rings a bell, but refresh my memory.
Think of it like a library with multiple reading rooms. Some rooms will give you faster access to certain bookshelves, right?
Right, so depending on where you are, you might have to walk further to get your book.
Exactly. In a UMA system, different processors have quicker access to certain parts of the memory. So the physical location of the data actually matters for performance.
So it's not just who's handling a task, but where the data for that task is located. Load balancing just got a whole lot more complicated.
You said it. An NUMA-aware scheduler has to consider not just how busy a processor is, but also memory access times. Moving a task to a less busy processor might seem smart, but if it means accessing data that's far away, it could actually slow things down.
It's like thinking you're being helpful by sending a chef to a less crowded station, but then they have to run across the kitchen for every single ingredient.
Exactly. It just shows how much intricate thinking goes on behind the scenes to keep everything running smoothly. Balancing processor load, memory access, and affinity. It's a constant juggling act.
It's mind-blowing how much is happening under the hood of our devices, and we don't even realize it. We just expect our computers to work, and they do. But there's more to it, isn't there? What about heterogeneous multiprocessing? HMP.
You're right. We can't forget HMP. So far, we've been talking as if all processors are the same, but HMP flips that idea on its head.
Ooh, this sounds interesting. So what makes HMP so special? What's the difference?
Imagine you need to transport something. You wouldn't use a huge truck to deliver a pizza, would you? You'd probably use a scooter or a small car. HMP works on a similar principle. It uses a mix of powerful big cores and energy-efficient little cores.
Okay, I like that analogy. So the big cores are like the heavy lifters, and the little cores are the nimble, efficient ones.
You got it. Big cores are great for those bursts of speed, but not very energy efficient. Little cores are perfect for everyday tasks, sipping power, maximizing battery life. And the beauty of HMP is that our devices can seamlessly switch between these core types depending on what we're doing.
So when I'm just browsing the web, my phone is probably using those little cores, saving battery. But when I fire up a game, it kicks those big cores into gear.
Exactly. HMP allows for a whole new level of power management and performance optimization that you wouldn't get with just one type of processor.
I have to say, my brain's starting to feel a bit like an overloaded processor trying to keep up with all of this.
I hear you. It's a lot to take in. Maybe a good time for a quick recap before we jump into the future of multiprocessor scheduling.
Phew, okay, my brain is still buzzing from all of that. We've covered so much ground in this deep dive into multiprocessor scheduling. From those multi-core CPUs with their hidden layers to this incredible dance of managing big and little cores with HMP.
It really shows how much ingenuity goes into making our devices run smoothly, doesn't it?
Absolutely. As we wrap things up, let's recap those key takeaways. We started with the idea that a multiprocessor isn't just about having multiple physical processors anymore. It's about the design of the CPU itself.
Right. And that led us to the core of multiprocessor scheduling, those two main methods, asymmetric and symmetric multiprocessing.
Asymmetric multiprocessing, that was like our head chef delegating tasks. And then we have symmetric multiprocessing, or SMP, where each processor is more independent.
And with SMP, we got into those fascinating ideas of queues, processor affinity, and the all-important warm cache.
Right. Making sure the data is close at hand so those processors can work their magic.
It's all about efficiency.
Yeah.
And just when we thought we had it all figured out, we added UMA to the mix, the idea that not all memory access is equal.
Like that library analogy, sometimes you have to walk further to get the book you need.
Exactly. And finally, we explored HMP heterogeneous multiprocessing, where not all processors are created equal. Different tools for different jobs.
And a total game changer for power management, especially for our mobile devices.
It really makes you wonder what's next for multiprocessor scheduling, doesn't it?
It does. As software gets even more demanding and hardware keeps advancing, what new challenges and opportunities will emerge? It's like a constant race.
A race that keeps computer scientists and engineers on their toes. We're already seeing specialized processors designed for specific things like AI or graphics. How will those fit into future multiprocessor systems?
Ooh, good question. So many possibilities. Who knows? Maybe we'll need a follow-up deep dive to explore all of that.
I'm always up for a good deep dive. But for now, I hope this episode gave everyone a good understanding of how multiprocessor scheduling works.
Me too. And next time you're using your computer or phone, take a moment to appreciate the invisible magic happening behind the scenes. All those processors and threads working in perfect harmony.
It's pretty amazing.
It really is. So until next time, keep those processors humming and those brains buzzing. Thanks for joining us on this deep dive.
Ever feel like you're juggling chainsaws? While simultaneously trying to defuse a bomb. And the bomb is also a souffle that's about to collapse.
Yeah, maybe not exactly that.
Okay, but you get the idea. Things needing to happen right now under pressure. And guess what? Computers feel that pain too, which is where today's deep dive comes in.
Yeah.
We're looking at your research on real-time operating systems, RTOS, for the cool kids. Basically, how do computers handle those moments when timing is everything?
What's fascinating here is that we're not talking about deadlines. You can stretch a bit.
All right.
Like replying to an email, we're talking milliseconds, even microseconds.
Wow.
The pressure's really on.
So no procrastination allowed for these systems. But seriously, how does a computer even know what has to happen instantly versus what can wait a bit? Like, is there a digital panic button?
You could say that. It all comes down to the difference between soft and hard real-time systems.
Yeah.
Imagine you're playing a rhythm game on your phone.
Oh,
Hitting the notes a little late might mess up your score, but the game keeps going. That's soft, real time. Now, picture those anti-lock brakes we talked about. They absolutely have to react instantly to prevent an accident. That's hard, real time.
right.
No room for error.
Okay, that's a much clearer way to think about it.
Yeah.
But it makes you appreciate how much those systems are doing behind the scenes, right? Especially if it's a life or death situation like in your research.
Exactly. The text mentions anti-lock brakes need to react within 3 to 5 milliseconds. To put that in perspective, that's less time than it takes for a hummingbird to flap its wings once. And that speed is all thanks to minimizing something called latency.
Latency. Okay, back to the video game analogy for a sec. That's basically a lag, right? Except instead of a frustrating pause, it's potentially a disaster.
Precisely. Latency is simply the delay between a command and the response. In our everyday lives, we don't notice tiny amounts of latency, but for these real-time systems, especially the hard ones, every microsecond matters.
Okay, so we've got all these time-sensitive tasks happening at lightning speed. How does the RTOS decide who gets to go first? It's like a digital mosh pit in there. But instead of elbows and bad dance moves, we're talking lines of code all vying for attention. How does the RTOS actually decide which task gets to be the VIP?
It's all about having a really good bouncer, and by bouncer, I mean scheduling algorithm. The research mentioned two big ones, rate monotonic and earliest deadline first. Think of them as different strategies for managing the chaos.
Okay, so rate monotonic. The name kind of gives it away, but I'm guessing it's all about how often a task needs the CPU's attention.
You got it. It's like giving frequent flyers priority boarding. The shorter the deadline a task has, the higher its priority. Let's say you're designing a system to monitor a patient's heart rate. That needs to be checked very frequently, right?
Absolutely can't miss a beat, literally.
Exactly. So with rate monotonic, those heart rate readings would get priority over something less urgent, like updating the display on the monitor. Figure 4.8.5 in the research shows this in action, with the task having a shorter deadline and shorter processing time getting prioritized.
Makes sense. But isn't there a chance this approach could lead to some wasted CPU time? Like if those frequent flyer tasks are really short, maybe some other tasks could sneak in while the CPU is waiting for the next heart rate reading.
That's a great point. And it highlights one potential downside of rate monotonic. It's very focused on frequency, which can sometimes lead to the CPU being underutilized. That's where earliest deadline first scheduling swoops in with a slightly different strategy.
Okay, and I'm assuming this one is all about, well, the closest deadline wins.
You know it. Imagine you're at that airport date again. But this time, the gate agent prioritizes whoever has the closest connecting flight, regardless of how often they travel. Figure 4.8.7 from the text illustrates this perfectly.
So it's less about how often you need the CPU and more about how urgently you need it right now.
Exactly. Let's say you have two tasks. Task A needs 10 milliseconds of processing time and has a deadline of 20 milliseconds. Task B only needs 5 milliseconds, but has a deadline of 15 milliseconds. With earliest deadline first, Task B gets priority because its deadline is closer, even though it needs less processing time overall.
Ah, so it's like a triage system for digital tasks. Makes a lot of sense.
Yeah.
But I'm already imagining how complex this could get, with dozens, hundreds, even thousands of tasks all competing for attention. Are there ways to fine-tune things even further? You're telling me. It's already making my head spin a bit. It's like trying to direct traffic in a city where every car thinks it has an emergency.
And that's where things get really elegant, because you're right, sometimes it's not enough to just prioritize by deadline. What if you want to make sure certain tasks or even certain users get a guaranteed chunk of the CPU's attention?
Ooh, okay, I see where you're going with this. It's like having different levels of VIP access at a concert, right? Some people get backstage passes, others get premium seats, but everyone gets their designated space.
That's a great analogy, and that's essentially what proportional share scheduling is all about. Instead of just looking at deadlines, it lets you slice up that CPU time pie into very specific portions. The research mentioned this idea of shares, like dividing up 100 shares among different tasks or users.
So if we think about that cloud computing example from the research, one user with a super demanding video editing program doesn't just get to hog all the resources and leave everyone else lagging.
Exactly. Proportional share scheduling lets you say, okay, video editor, you get 50 shares. But our spreadsheet guru over here still needs their fair share to keep working smoothly. It's about ensuring fairness and preventing any one task from completely taking over.
It's like having a super organized party host who makes sure everyone gets a turn to chat and no one feels left out. Makes you realize how much thought goes into keeping our digital lives running smoothly. So as much as I'm loving this deep dive into the world of real-time scheduling, I have a feeling we've just scratched the surface, haven't we?
We have indeed. We haven't even touched on things like POSIX scheduling, which adds a whole other layer of complexity, or how these algorithms get implemented in specific RTOS. It's a vast and fascinating field.
And one that's easy to take for granted because it's all happening behind the scenes, making sure our devices can keep up with our need for speed. Speaking of which, for anyone listening who's now as hooked on this topic as I am, we'll be sure to link to some further reading in the show notes. But before we go, any final thoughts to leave our listeners pondering?
How about this? We've talked about anti-lock brakes, heart rate monitors, even cloud computing. But imagine these scheduling algorithms at work in a Mars rover, millions of miles away. The environment is harsher, the stakes are higher, and every decision is mission critical. How do you think those factors might influence how you approach real-time scheduling?
Ooh, now that is a question to ponder. Suddenly, my deadline to finish this podcast script feels a little less intense. Thanks for joining us on this incredible deep dive into the world of real-time scheduling. It's been eye-opening to say the least.
The pleasure was all mine. Until next time. Ever find yourself wondering what's really going on inside your computer? Like when you open an app or you're waiting for, a website to load. It's not magic. It's CPU scheduling algorithms, and they're working behind the scenes to, make sure everything runs smoothly.
Right.
So today we're taking a deep dive into this surprisingly crucial aspect of how your devices actually work. And trust me, you'll come away with some serious aha moments.
I think so.
We're going straight to the source. A textbook on operating systems. We're going to break down the complexities of CPU scheduling algorithms, and we're going to understand why they matter so much in our daily digital lives.
Yeah, it's like having a conductor leading a symphony orchestra.
Okay.
Making sure that each instrument gets its moment to shine without a single beat out of place.
I love that analogy. Okay, so instead of instruments, we've got lines of code all vying for the CPU's attention, right?
Yeah.
The CPU is the conductor in this case. Can you give us a quick definition of what exactly these CPU scheduling algorithms do?
Absolutely. CPU scheduling algorithms basically decide which software processes or tasks get access to the CPU and in what order. So it's all about managing the CPU's like time and attention to ensure that your computer can handle multiple tasks efficiently and effectively.
So if my phone feels sluggish or like a website is taking forever to load, it could be that my CPU is struggling to juggle all those processes.
Exactly.
Okay.
A poorly chosen or implemented scheduling algorithm can lead to those those frustrating slowdowns and lags that you get. It's like having a traffic light that's always red at the busiest intersection.
Oh, yeah.
And it's not just about speed. Like think about video calls or online gaming, where even a tiny delay can ruin the experience.
Right.
Those scenarios demand like real-time responsiveness.
Yeah.
And that's where clever scheduling becomes really important.
That makes a lot of sense. Now, our source mentions a few key metrics used to evaluate how well these scheduling algorithms are doing their jobs. Things like CPU utilization, response time, and throughput. Could you unpack those for us and maybe connect them back to that user experience, how we actually perceive these behind-the-scenes operations?
Sure. So CPU utilization, basically it measures how much of the CPU's time is actually spent doing work versus sitting idle waiting for instructions. So ideally, we want to keep the CPU as busy as possible. We want to maximize its utilization to get the best performance.
So high CPU utilization is generally a good thing. It means our devices are working efficiently.
Exactly. Now, response time measures how long it takes for a process to get the CPU's attention, basically, from the moment it's requested. So in our conductor analogy, it's like, how long an instrument has to wait before the conductor acknowledges them and allows them to play.
Okay.
A slow response time would be like that awkward silence after someone tells a joke.
Right.
Not a good look.
No. So faster response time, snappier, more responsive user experience.
Yeah.
Got it. What about throughput? What does that measure?
So throughput focuses on the overall efficiency of the system. It's like asking, how much work is this CPU actually getting done over a specific period?
Okay.
A higher throughput means that the system can handle more tasks in the same amount of time, making it more productive.
It's amazing how much complexity goes on behind the scenes, even for the simplest actions on our devices. I had no idea so much thought and strategy went into something like deciding which task the CPU should focus on.
It really is. It's a testament to the ingenuity of computer scientists and how these systems are designed. And just like there are different strategies for winning a race, there are different approaches to CPU scheduling. Each one has its own strengths and weaknesses depending on what you're trying to achieve.
So you're saying there's no single best scheduling algorithm. It's more nuanced than just finding the one that's universally the fastest or the most efficient.
Yeah, exactly. You hit the nail on the head. The textbook dives into a few methods experts use to evaluate these algorithms, and it's kind of like comparing, apples to oranges. Each method has its own perspective. They've got their own strengths and limitations.
Okay.
Yeah.
Let's explore those methods. I'm curious to see how these evaluations actually work, in practice. What's the first one?
So one approach is something called deterministic modeling. It's basically like creating a perfectly predictable simulation where we know exactly when each task will arrive and how long it will take to complete.
So it's kind of like those, model train sets where you lay down the tracks and you set the schedules for each train. Everything's like controlled and predictable.
Precisely. And within that controlled environment, we can then experiment with different scheduling algorithms, and we can see how they impact key metrics, like, for example, waiting times.
Okay.
So, for example, the textbook highlights how an algorithm like shortest job first, or SJF, can significantly reduce the average waiting time for processes compared to a simpler approach, like first come, first served, or FCFS.
So with SJF, the CPU prioritizes the quicker tasks, which then leads to a faster overall experience. That makes sense, intuitively.
It does, but of course, real-world computer systems they're rarely as predictable as a model train set.
Right.
And that's where deterministic modeling stumbles a bit. It's a great starting point, for understanding the core concepts, but it doesn't quite capture the messy realities of how we actually use our devices.
Right. Our digital lives are very rarely that organized and predictable.
Right.
So what's the next method on the list? How do we make these evaluations more realistic?
So that's where queuing models come in. Imagine for a moment like a busy supermarket checkout line.
Okay.
Customers arrive with their baskets full of groceries, and each one requires a certain amount of time to be processed by the cashier. Queuing models use mathematical formulas, and they use probability to predict how those checkout lines will behave, based on factors like the rate at which customers arrive, the average time it takes to serve each one.
So it's like trying to predict how long you'll be stuck in line based on like how many people are ahead of you and how fast the cashier is working.
Exactly. And one of the key formulas that's used in this method is called Little's Law. And while it sounds intimidating, it essentially helps us understand the relationship between the average number of customers in the queue, the rate at which they're arriving, and the average time that they spend waiting.
Okay, so even though it's based on math, we can understand the essence of Little's Law without needing to be mathematicians ourselves.
Right.
It's about those relationships, the waiting, arrival, and service times. But I'm guessing even queuing models have limitations when it comes to something as complex as CPU scheduling.
Yeah, you're right to be skeptical. While queuing models offer, really valuable insights, they often have to make assumptions about arrival patterns and service times, which aren't always accurate in the context of like ever-changing computer systems.
Right.
Our digital lives are full of unexpected interruptions and tasks popping up, making it hard to predict those patterns with perfect accuracy.
So how do we get closer to that real-world accuracy? What's the most sophisticated method that these experts have up their sleeves?
Well, if deterministic modeling is like using a model train set, and queuing models are like analyzing supermarket checkout lines, then the next level up is full-blown simulation.
Okay.
Imagine like those city traffic simulations you see in documentaries where they're testing out different traffic flow patterns. We can do something very similar for CPU schedule.
Oh, wow. So we create a virtual replica of a computer system and then unleash various scheduling algorithms upon it to see how they perform in a simulated real-world environment.
Yeah, you got it. And just like those traffic simulations rely on real-world data about road conditions and driver behavior, CPU scheduling simulations can benefit from using actual data collected from real systems. So we call this data trace files. They're basically like recordings of how tasks behave in the wild, so to speak.
So it's like having security camera footage of the CPU in action.
Exactly.
We can see exactly how it handles these different tasks under different conditions. This sounds like the most accurate method so far, but I have a feeling it's not as simple as just hitting like a play button on a simulation and calling it a day.
You're right. There's always a trade-off. Simulations can be very computationally expensive.
Okay.
The more detail and accuracy that we want, the more processing power and time it takes to run those simulations, and then also to make sense of all the data that they generate.
So it becomes this like balancing act between achieving that real world accuracy and then like managing the complexity and resources required for these simulations.
Precisely. And sometimes a simpler approach, even with its limitations, might be more practical, especially, during those initial stages of designing and testing these algorithms.
Okay, so we've explored these like fascinating evaluation methods, from model train sets to supermarket checkout lines to like full-blown city simulations.
Right.
It's amazing how much effort goes into understanding and optimizing these algorithms. But at the end of the day, we need to take these algorithms out of the textbook and actually implement them in real operating systems. That sounds like it comes with a whole other set of challenges.
Absolutely, yeah. In fact, the textbook actually says that implementing an algorithm in a live operating system is the only way to truly know how it's going to perform.
Yeah.
But as you can imagine, it's not a task for the faint of heart.
I can imagine. It's like trying to change a tire on a moving car. The system's constantly running, users are interacting with it, expecting things to work smoothly.
Yeah, that's a very apt analogy. And just like with that moving car, even the slightest misstep can have, unintended consequences. So developers have to be incredibly meticulous. They have to make even the smallest changes with extreme care, because a tiny tweak to the scheduler could cascade into, major issues throughout the entire system.
So it's not just about making the scheduling algorithm work in isolation. It's about making sure it plays nicely with all the other components of the operating system.
Precisely, yeah. That's where something called regression testing comes into play. It's like after you change that tire on the moving car, you want to make absolutely sure you didn't accidentally mess up the brakes or the steering in the process, right?
Right.
Regression testing ensures that while we're focused on improving one aspect of the system, we're not accidentally, introducing new problems elsewhere.
Makes perfect sense. It's all about those unintended consequences, like that fascinating anecdote from the textbook about the programmer who found a clever loophole in the system.
Oh yeah, that story, that's a classic example of the cat and mouse game between the people who design these intricate systems and those who find, ingenious and sometimes mischievous ways to use them.
Just to refresh our memory, this programmer realized that the system prioritized tasks that interacted directly with the terminal, assuming that they were user-facing and therefore more urgent.
Exactly, yeah.
Right.
It was a reasonable assumption. But this programmer figured out how to game the system.
By making their program send a meaningless character to the terminal every second, just to trick the system into thinking that it was like super important and deserved priority. I have to admit, I kind of admire their ingenuity.
Yeah, it's certainly a creative use of their understanding, right? But it also highlights why flexibility and adaptability are so crucial in scheduling algorithm design. As we use our devices in more and more complex ways, and as new technologies emerge, the demands on these algorithms, they continue to evolve.
Yeah. Makes you realize that behind all this tech jargon and this complex code, there are real people making decisions, writing these algorithms, and sometimes even trying to outsmart each other. It's a reminder that technology is never truly objective.
It's a great point. Technology is shaped by, the people who create it, the people who use it, and the often unpredictable ways those interactions kind of unfold in the real world.
So what does all this mean for us, the everyday users, right? Most of us aren't going to be like coding our own CPU scheduling algorithms anytime soon.
True. But even a basic understanding of these concepts, it gives you a new appreciation for what's happening inside your devices. The next time that your phone feels sluggish or an app takes a while to load, you'll have a better sense of the intricate dance that's happening at the heart of your computer. Maybe even a bit more empathy for those who dedicate their careers to making this digital symphony play smoothly.
Yeah, it's like having a secret decoder ring for the digital world. We can peek behind the curtain and we can understand the forces that are shaping our experiences.
Precisely. And as we move further into the future of computing, with the rise of like artificial intelligence, virtual reality, and who knows what else is on the horizon, the demands on CPU scheduling algorithms are only going to intensify. These emerging technologies, they require immense processing power, and ensuring that our devices can handle those workloads efficiently, it's going to require increasingly sophisticated scheduling strategies.
That's a fascinating thought to leave our listeners with today. As we demand more from our devices, how will we ensure that our computers, our phones, our tablets can keep up? It's a question that will keep computer scientists, and now perhaps you, pondering for years to come.
And who knows, maybe one of our listeners will be inspired to tackle these challenges and shape the future of computing.
That's all the time we have for today's deep dive into the fascinating world of CPU scheduling. Thanks for joining us for this journey inside your devices. We'll catch you next time for another exciting exploration of the tech that shapes our world.